So today I'd like to start out with a question that we postponed earlier this term and see if we can come up with a good algorithmic answer to it. And the question that I posed earlier was, how large should a hash table be? Okay. So how large should a hash table be? Any ideas? Yeah.
Slightly larger than the expected number of elements during the pool?
Yeah, so it could be big enough, but not too big, right? So, large enough that it doesn't overflow or be inefficient. That's part of it. Okay, so I'll just make a huge hash table. I don't want to do that either. Why? Yeah, takes up more memory. Memory's a resource that's of limited supply, especially fast memory. Okay, so we'd like it to be as small as possible. Okay, so that's pretty simple. But what if we don't know the right size in advance? How big do we make it if we don't know? So for example, suppose that I have, I say, okay, let me make a hash table with 10,000 entries. What's the asymptotic performance of that hash table for doing a query on, if I have n items? If I have n items that I'm going to store in a hash table, I have, say, resolving by chaining. Let's say I have 10,000 slots. What's the asymptotic performance? Yeah. Yeah, order n as n approaches infinity. I mean, there's a much smaller constant there than there is if I used a linked list, but it's basically asymptotically the same thing. Okay, so picking any fixed size is only staving off the ultimate growth problems that we're going to have. Okay, so the trick is don't use a fixed size table. And the solution we're going to look at is sometimes called dynamic tables. And this applies not just to hash tables, but any kind of table that we want to use. And you'll see actually the ideas are even more general than that. So here's the basic idea behind dynamic tables. Okay. Whenever the table overflows, or would overflow, we're going to grow it. And we're going to do that by allocating. And this is in C, you use the call malloc, or in something like Java, I guess it's new. Is that right? Yeah. Okay. That's how you allocate stuff. We allocate a larger table. And then we'll move the items from the old table to the new one. And then we'll free the old table. Okay, so let me give you an example of that. Okay, so here's a table. We start out, say, with table size 1. Okay, and our first step is to do an insert. So here what I'm going to do is we're not going to really look at it as if it's a hash table, because we're not really concerned with the hashing behavior. We're just concerned with the size of the table compared to how many items are in it. Okay, so I'm going to use a much more compact representation. In fact, this could be a stack or a FIFO queue. It could be, there's a whole bunch of different things that this table could be storing. It could be just an array. In fact, the programming language CLU, CLU, which used to be taught, the language that was taught in 6170 before they started using Java, okay, had a nice feature, which was that it had arrays that you could extend. So you didn't have to declare an array of a fixed size. If you wanted it to be longer, you just said, OK, extend this array. It would extend the array. Very simple. And it basically used this idea. So we say insert. And so we put an item in there. And then we say insert a new item, so second operation. And what we discover is it overflows. It won't fit. So what we do is we allocate a new table. In this case, we'll allocate it of twice the size. And then we copy the one in there, and now we can put 2 in. Okay? Then we do another insert. Okay, and we discover, oh, overflows again. Okay, so we make an array of size 4. Okay, we're going to double it every time. Okay, we copy these guys over. Now we can insert 3. Now we insert again. We have 4. No overflow that time. That was good. Starting to think we overflowed every time. Okay. Do another insert. Okay, and we get an overflow again. So we make an array of size 8. We copy these guys all over. And then we insert the 5th element. Okay, and then the thing is that we can go ahead and insert, the 6th element, the 7th element, okay, and they just go in, okay, and so forth. And when we hit the 9th element, we'll copy it again. So let's analyze this. Okay, is this a good method? Okay, so we're doing a sequence of n insertions. Okay. What's the worst case cost of one insertion? If we do n insertions, what's the worst case cost for one insertion? Order n, right, because it might be the case that that's the one that causes the overflow, in which case everything has to be copied over. That'll take me order n times. So the worst case cost of one insert is order n. And so therefore, since I'm doing n inserts, the worst case cost of all n inserts is let me just write it out, is, since there are n of them, and the worst case for one is order n squared. That doesn't look like too good a method. Okay. Yeah.
But you're not going to have all of them be worst case.
Oh, how about that? I'm not going to have all of them be worst case. Yeah. In fact, this always when you get a bad analysis, you have to ask, is my analysis bad or is my algorithm bad? Here's a case where the analysis is really bogus, right? This is wrong. Okay, whereas my kids used to say, not. Okay, this is not right, okay? Because I can't have the worst case for every single one. In fact, what is the worst case time for doing n inserts? Excuse me? Order n. Yeah. Okay. Okay. In fact, it only takes order n time. Okay. Even though I'm doing all this copying, and even though the worst case is order n, also to do n operation turns out to take order n. We're going to spend now, this is a very simple example, and some of you, as I can see, can look at this and say, oh, that took order n. Okay. We're now going to go through a bunch of different ways of showing that this is order n. Okay? And each one is going to teach us something more about the kind of analysis that we do here. It's called amortized analysis that we do to understand the performance of things like this. Now, this is a very simple example. Okay? And we're going to see through the term now, we're going to see other examples coming up where the analysis gets harder and harder. Okay? And yet, by using some of the techniques, in fact, you'll look at some of the techniques that we present today, and you're going to say, why would you go through all that hassle? Well, the answer is because that's actually simple, okay, in some contexts. Okay, so let's do this analysis. We'll start out with sort of the most straightforward type of analysis to get this bound of order n for n operations. So let's let C sub I be the cost, that is the time, of the ith insert. Okay? So that's equal to, I claim, I, if I minus 1 is an exact power of 2, and 1 otherwise. So here I'm using the cost to be sort of, I'm throwing away whatever constants are involved and just sort of looking at the cost to sort of do a constant amount of work is I'm calling 1. Okay? So let's just look and see if that's in fact what was the case. So certainly 1 most of the time. I just do a constant amount of work stuffing it into the table. And then occasionally I double it. Every time I double it, I'm at a power of 2 plus 1. Right? So I doubled at 2. I doubled at 4. Excuse me, I doubled at 3. Sorry. Yeah, I doubled at 2, doubled at 3, doubled at 5. I'm going to double again here at 9. It's always a power of 2 plus 1. And so therefore, if I minus 1 is an exact power of 2, that's when I'm going to do a certain amount of work. And the work is going to be proportional to the total elements in the table at that time. That's I. So I can claim that this is what the cost is, the actual cost of doing these operations. People follow that? Okay. Okay, so let's track, just for this example, let me make a table. Actually, I'm going to make a table on a different slide, because this table, I'm going to provide a few lines. I'm going to add a few lines later when we see one of the other methods. So if you are taking notes, you will want to leave a little bit more space than what I actually write down. So we're going to have I. We have the size of the table. Let's call that size sub I. Okay, and we're going to have C sub I. Okay, so I know how I goes. I goes 1, 2, 3, So we'll go up to 10, say. Okay? And how does the size go? So after the first operation, how big is the table? 1. After the second operation, 2. After the third, 4. Because to do the third operation, we had to double the size of the table. Okay? 4 again. 8. 8. 8. 8. 16. 16. Okay, so you get the idea. Okay, good. So what is C sub I now? What's the cost for this one? 1, 2, 3. Good. 1, 2, 3. I'm hearing. I know some good jokes about 1, 2, 3. Okay. 1. Good. 5. 'Good. Okay, everybody following that? So those are sort of the actual costs. I actually want to break this down. So I want to rewrite this line here as having 2 parts. So one part I'm just going to make 1 because it makes it easier to see what's going on. Okay? And what I want is the sum of these 2 things to equal this line. So I always have to pay for the insert of the thing I'm inserting. And the question is, what's the other overhead in copying? So in the first step, there's no overhead. The second step, I have 1 unit of overhead to copy, to move the elements. What about for the next one? 2. See, I'm just making these 2 things add up to that. Okay, here, 0, 4, 0, 0. Everybody's looking at me quizzically as if, can't you add up? Okay, 0. 8, good. 0. Okay, and now the pattern becomes really obvious. Okay, that there's basically just 1 plus, and now what type of sequence am I getting from the non-zeros here? Powers of 2, which is geometric. I don't know why they call it geometric. Geometric would seem to be like quadratic or cubic, you know, because geometry is sort of like, you know, if I grow the diameter of something, the area squares or the volume cubes or something. That would seem to me to be geometric. But for some reason, they call geometric when it's going up as an exponential amount. But that's not geometric. I don't know. Those mathematicians, I think. You have to question. See, everything that's done in mathematics is human generated. So you always have to question, because they're just humans, just like you and me. Okay? And sometimes they, you know, they didn't get the definitions right. Okay. So let me flip back up to this board here. So I'll leave a couple lines here, because I have a couple more lines I'm going to put in later. Okay. So the cost of n inserts is summation I equals 1 to n of C sub I. Okay, just add them up. And that's at most, I claim by this observation, n for adding up all of the 1s, if I do n inserts. Okay, plus, okay, the sum of a geometric series of 2 to the j, where j starts out at 0, and what does it go up to? Something like log n, but you know, if you're going to be a good algorithmicist, you have to be more precise than that sometimes. Sometimes asymptotic works. Sometimes you got to deal with the constant. Sometimes you got to be exactly right. I want right on. What is the number that goes here that's exact all the time? Yeah. Floor of log n. That's very close. +1, -1. And plus, there's all these places I could put it. I could put it floor of log n, close the floor, -1, or I could have floor of log n -1. I could have the floor of log of n -1. I could have the floor of log of n +1, the floor of log of n +1. Any other places I could put the plus, -1s that I'm hearing from the audience? Okay, vote. Okay, so I did this with my Singapore students last night. Okay, we had a democracy. Okay, so how many people vote for, and by the way, the people who didn't vote, those were the people I called on. Okay, so you want to vote, okay, unless you want to be called on. Okay, so how many people vote for floor of log n -1? Okay, how many people vote for the floor of log of n -1? Ooh, about half the class. That's big. Okay, how many vote for floor of log n +1? 1. Okay, 2. Okay. How many vote for the floor of log of n +1? Okay, just a couple sort of hesitant. Am I the only one? Okay, I think this is it. That's the one that the majority chooses anyway. And the question is it right? I think it is. That's the one I picked anyway. Let's see why that is. Okay, so we're basically going up. We want the case where it's going to trip over to the next higher number. When? When n -1, which is an exact, it's going to trip over when n -1 is an exact power of 2. Okay, that's when it trips over to the next next larger values. Okay, so therefore this is what I want for my number. If I haven't made it up to the next, to one more than the next power of 2, I don't want to add on another term. Okay? And think about that. I don't think I explained that very well. This is one of these things maybe you have to study a little bit. Sorry. Okay. But it doesn't really matter, because whatever one we picked here, we would get essentially the same answer. So this is at most what? Yeah. The whole thing. The whole thing. What's the whole thing at most? (2n). Boy, doing math in the morning is... Come on, this is fun. Right? We're cranking through algebra. This is stuff we did in high school. Right? Didn't we do summations in high school? So remember, we got n plus this. 3n, good. 3n, excellent. Okay. Okay, which is order n. Okay, because this is a geometric series. Okay, and I could write out the formula and so forth, but this term here is at most 2n. Okay, most 2n. Okay, we set. So the whole thing is at most 3n. Everybody with me? So the average cost per insert, what's that? That's just theta n over n, which is order 1. And so this is where we get into the topic of amortized analysis. Because what I would like to do is, if I had to present this data structure to a user, what I'd like to tell the user is, just think of every operation as costing a constant amount, because on average, that's what it costs. Okay? Just costs a constant amount to do an operation on this data structure. Now, it may be that as the program is running, there are certain times where it takes longer than other times. But overall, if he adds up over his whole use of that data structure, he's going to discover n operations took order n time. So it really simplifies the performance understanding of the data structure to be able to say that the cost of the use of this data structure was 1. If you went with that assumption and did all your mathematics on the outside with whatever algorithm was using this data structure, you'd get the right answer. Okay? You'd get the right answer if you used order 1 for each operation, rather than using this far more complicated formula that's hard to understand. You give a user this, right? Then they go through what we just went through. Okay? You give a user this, they say, oh, okay. Okay? So that's kind of cool, right? It's major simplification and sort of encapsulating the performance attributes of a data structure is to say, in this case, cost constant time per operation. That's all there is to it. Okay? But it doesn't really cost constant. What we say is it costs, the amortized cost is a constant. Okay? So we relabel it so that people know that, yeah, some operations could cost a lot, okay, but on average over n operations, it's going to cost a constant. So let's talk a little bit about amortized analysis. Sort of overall, and then we're going to see several ways of doing amortized analysis that have been developed and that are, really quite neat things. Okay. In England, they spell it with an S, by the way. Okay. So the idea of amortized analysis is to analyze a sequence of operations, typically on a dynamic set or other data structure, to show that the average cost per operation is small. Even though one operation may be expensive. Okay? That's typically what we're doing when we do an amortized analysis. We're trying to show that some aggregate behavior, that the overall thing is small, even though one may be expensive. Okay? And one of the things that sometimes people get confused about when they're doing is we're talking about average costs, but there's no probability in the definition of amortized in an amortized analysis. We're talking about the average performance of operations in the worst case. In other words, the average is taken over the number of operations. We're not taking the average over some probability distribution. No assumption about a probability distribution. There's no probability space here. We're just saying there's n operations, and we're taking the average over the n. Okay, so don't get confused when we do amortized analysis. We're talking about the worst case performance, generally. Okay? There are 3 types of amortized arguments that you'll find in the literature. So sort of if you look overall, you can sort of break them down into 3 major types of arguments that have been used. Okay, the first is what's sometimes called an aggregate analysis. Okay, and this is the method that we just saw. Okay, I simply analyze what did my n operations cost me. Okay, so we do an aggregate analysis. Okay, the other two methods that are used we're going to see in a moment. One is called the accounting method. Okay, and the other is called the potential method. Of analysis. These two are more precise than the aggregate. And in particular, one of the things that happens in an aggregate analysis, here it's not so hard because we can say that the cost, the amortized cost of an operation is constant. Okay, instead of this hairy function, and it makes sense. But generally, in more complicated settings, it's hard with an aggregate analysis to assign a specific amortized cost to a specific operation. Whereas the accounting and potential methods let us assign specific costs to individual operations. Okay, so these, and that turns out to have a big advantage in sort of this encapsulation of the performance attributes of a data structure. Okay, that's a big advantage. So we can allocate specific amortized cost to each operation. Okay, so that's one of the nice things about these other methods. So you're going to see that this, using the accounting method or the aggregate method is a little bit, the accounting method or the potential method is really a bit of overkill on the dynamic table instance. Okay, now when you do expansion and contraction, so suppose you start deleting items from the table. You would like, as the items are deleted, you'd like, when it gets smaller, to free up the large space and use the smaller space. Okay, that would be a helpful thing to be able to do. Okay, and that is dealt with in the book. Not a question, just a stretch. Okay, good morning. Did you do your yoga this morning? Okay. When you want to contract it, you can think about that a little bit. And when would I want to contract the table? How few elements would I want in the table before I contracted it in order that the amortized cost would still stay a constant for an insertion or a deletion? So when it overflows, we're going to double it. Okay. When do I want to have it? When it's half the number. So that sounds okay, but I could run in the situation where I go to, it overflows, right? So I double it. Now I immediately delete something. Now it dropped below half. So then I collapse and copy them all again. Now insert, double it, copy them all again, delete, have it, and boom, 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 boom. Okay, so a half is not where I'd want to do it. 3/8? Yeah, 3/8 will work, or any fraction, constant fraction less than a half will work. Okay, like a quarter or 3/8. Any number like that would work. Okay, and the book has some analysis of that, so I encourage you to read in the book about expansion and contraction. For that, it starts to get more useful to use these other approaches because you don't know which operations in what order some user of your data structure is going to have them. With inserts, it's very easy to do an aggregate analysis because it's all the same thing. But if I don't know how many insertions and deletions and when they occur and so forth, It gets very tricky to sort of just do an aggregate analysis. Okay, let's start out with the accounting method. Okay, and so we've seen the aggregate analysis. So now we're going to do an accounting method. And here's how that method works. So this is sort of the mafia bookkeeper's method. That's another way of viewing it, okay? So the whole idea here is what we're going to do is we're going to start out where we ended up in this analysis. So we ended up saying, okay, so each operation on average cost 1. Okay, cost order 1. So what we're going to do is start out that way and say, let's charge each operation some fictitious amortized amount. Okay, so we're going to charge the ith operation a fictitious amortized cost C sub I hat, we'll call it, where $1 pays for 1 unit of work. That is, by work here I mean time in this case. For us to get 1 hunk of constant amount of work done. Okay, so we charge a certain number of dollars for each operation. Okay, and this fee is consumed to perform the operation. Okay, but it may not be completely consumed. There may be some left over. And if there's some left over, we put it in the bank. Okay? So the unused amount is stored in the bank. Okay? And now later operations can use it. So if a later operation we charge the fee and it turns out to cost more money to perform the operation than the fee that's being charged, then we dip into our bank account to pay the remaining cost of actually doing that operation. Okay? And the key thing, and this is why, to make sure that this scheme will actually work out, is you can't it's just like your bank account. Okay, what's the smallest amount you can have in your bank account? Right, okay. 0, right? I mean, if you go below 0, typically bad things happen unless you go and get credit and so forth. But we're not going to allow you to work on credit here. Okay? So the idea here is the bank account must not go negative. Bank balance. Okay, so can't drop below 0. In other words, it must be the case. I want to leave that up, and I want to leave okay, so we must have okay, so what does it mean for the balance not to go negative? How can we think about that in terms of doing the operations? What does that mean? Yeah. Yeah, it's actually, so if I take a look at the total costs that I've incurred, how does that relate to the amortized cost? Should be less than or equal to the sum of the amortized costs. Okay, and this should be true for all n. It's always true. Okay, that whatever I've expended for real, I've always paid enough up to that point to pay for it. Okay? So therefore, the total amortized costs provide an upper bound, since we're interested in upper bounds, on the total true costs. Okay, should be the case that as I'm doing all this bank accounting, okay, I can switch things around, you know, charge you a little bit even though it's going to cost a lot and so forth, and all that'll be fine, and the mafia accountant doesn't get sent to jail, okay, as long as he can make sure the bank balance never goes negative. If he can do that, then the mafia accounting is just fine. Okay? He's got a good front. Okay, nobody, the IRS doesn't suspect. Okay, FBI doesn't suspect, whatever. Okay. I guess I shouldn't be using mafia because that's ethnic, right? I mean, it's always connected with the Italians. So I should be using, you know, the Russian mafia or the Vietnamese mafia or the Chinese mafia or is there an Indian mafia? I don't know either. Okay. Anyway, so everybody follow this? Okay. So what's great about this sort of stuff is it's not that hard, but it's very mind-bending, as you'll see as we get into this a little bit deeper. Okay. It's very okay. So let's do this for dynamic tables. Okay, so the dynamic table, okay, what I'm going to do is $1 is going to essentially pay for an item to be inserted or to be moved. Okay, that'll be sort of the constant amount. So I'm going to charge $3 for the ith insert. Okay, so every insert gets charged $3. Okay, $1 pays for the immediate insert, and $2 are stored for table doubling when it occurs. Okay? And when the table doubles, okay, $1 will move an item that I've recently put into the table, and $1 will move an old item. So let me draw a picture of that over here. So here I have, let's say I'm at this stage, and generally what I'll have is I'll have no dollars at the for the first half, and because this is what happened from the last time that I inserted, and then I'll have $2 for every item that I put in after I've done the actual insert. So I charge it $3. Okay, so for the next item I put in, I charge it $3, $1 inserts it, and I have $2 left. So my bank account has $6 in it. And I insert another item. I insert it, $1 pays for the insertion, $2 left. Now I insert another item. We get an overflow. So we double the size of the table. There we go. Double the size of the table. And I copy all of these guys down. And how much does that cost me to copy all of those things? $1 for each, which is a total of 8 in this example. Okay, and how much money do I have to copy? 8. Okay, so I don't go, I don't violate the property that I have, no money, less than no money. So I copy those, and of course there's no money left here now. And then I insert the element that caused the doubling, which cost 1 to do the insertion, and I have $2 left over. And then I continue to 2, etc. Okay, so restoring the thing. When I get up to this point, I've accumulated enough money to pay for moving one of the recent items plus one of the old items for each $2 that I have here. Okay? So even though, this first guy here, he's going to get copied a lot. He gets copied log n times. Right? But he only pays for his own first copy. He doesn't have to pay for somebody else is paying to move him in the future. Okay? Or her. Okay. So the invariant that we're maintaining is that the bank balance is always greater than or equal to 0. And so therefore we can conclude that the sum of the amortized costs is greater than or equal to the sum of the true costs. And therefore charging a constant amount per item is perfectly okay. So I say, oh, I had n items to insert. That was constant amount per item. Okay, so constant amortized amount per item. I had n items. That cost me order n in the worst case overall. It doesn't cost me n amortized cost for the total thing. The total cost of the n inserts is worst case order n because I have this bound on the sum of the amortized cost. Let's just see how that works in this figure that I have up here. Okay, so let me put in C sub I hat and how much is in the bank. Okay, and in fact I lied. Since the first guy doesn't have to pay for anybody else, we're just going to charge him 2 instead of 3. Okay, it's bounded by 3. We'll charge him 2 because it'll make the what's left in the bank. So so the amount left in the bank, since it cost me 1, okay, if I look at this one, the amount left in the bank at that point is 1. Okay, so I have 1 item in the bank. Okay, then I do the insert of number 2, and it causes a table doubling. Okay, so I charge it 3. In fact, I'm going to charge them all 3. Let me put this row in. Okay. Okay. So how much is left in the bank after I consume the amount here? After I consume my fee for doing the insertion? Yeah, 2 is left in the bank. Okay. So my cost was 2. because I had to do the table doubling in a copy. Okay, so the total amount that I have brought in up to that point is 5, and the total amount it has cost me up to that point is 3. So that leaves me $2 in the bank. Okay, what about the next step? Now I insert the third item. How much is left in the bank? 2. Good. And the next one? Four. Okay, 4. Because I'm doing an insertion, but I don't have to do, it's only costing me 1. So I have $2 more I'm putting into the bank. Okay? So here now I get a table doubling. What does this come out to be? 2. If you think about it from the point of view of that thing there, whenever I double a table, I ought to be left with 2 because I've just done an insert. Okay? And here, 4, 6, yeah, because we're just adding $2 to the bank account for each of these inserts. 8, and now here, this 8 is paying for that, right? And so I'm left with 2, and then 4, 6, 8, etc. And so the point is that that this is paying for this in some sense, okay? And this one is paying for that one, okay? And this one is paying for that one, and this one is paying for that one. So all of the costs, additional costs that I incurred are paid for by the increase in the amount of money that I've put in the bank. I've saved for the rainy day. I know the rainy day will come. Okay, but if I save regularly, when the rainy day comes, I can handle it. Okay? So the key thing is it never drops below 0. So therefore, I get an upper bound by just adding up the amortized costs. Okay? Now, it turns out that there are different schemes for assigning costs that may work. So one of the fun things about amortized analysis is there's different ways you can push the costs over from one place to another. Okay, for example, it probably would work, I have to think about this, if I charged $4 for every odd operation and $2 for every even operation. Okay, or if I charged $6 for every odd operation, that is the odd indexed ones, and all the even ones are free. Why? Because each one paid for the next guy. Okay, that would be a perfectly good way of assigning amortized costs. Okay, there are a whole bunch of different ways you can assign amortized costs, and they will, but some of them will give you better bounds, and some will give you worse bounds. Some of them will explain more, some of them are just more complicated. Okay? Good. So in fact, actually, when we talked about table contraction, there are a bunch of different ones that work for table contraction based on whether you're doubling the table and when do you decide that you're going to contract the table. Okay? You can come up with schemes that will work if you decide you're going to triple the table. Okay? And so forth. So there are a whole bunch of different schemes that will work in amortized analysis. Okay. The third method that I want to discuss is arguably the most sophisticated of the three methods. And it's called the potential method. And it is used, is probably the most powerful of the three methods, although any of the methods are equivalent. It's really just, this is sort of a human thing of, a framework. But the potential method has been able to be used to solve problems that the other methods, people had a hard time applying them to be used, or the arguments got very complicated. And the way that that works is sort of, it's the opposite of the way that the accounting method works. The accounting method charges for each operation some amortized cost, and then you look at the bank balance. Okay, make sure it doesn't go negative. In the potential method, you start out the other way. You say what the bank balance is, and then you figure out what the amortized cost of each operation is. Okay, so you go the other way around. Okay, so let's look at this method. Okay. But in some sense, all these methods are equivalent. Okay, it's really just a question of which way is easier to do something. Okay, so here what we'll do is we take a look at the bank account. Okay, but what we do is we view it as potential energy. Okay, of our data structure, dynamic set. Okay, so if you've got a bunch of money there, that's potential. It's not doing anything for you, but it's like storing energy into a spring, for example. It's in a position now to do work for you. Okay, so we're going to view the bank account as having that potential energy, and we're going to use some of the lessons of physics for manipulating potentials, okay, in order to analyze, do amortized analysis. That's why I say this is sort of mind-bending in some ways, because suddenly we're going all the way from finance to physics, right? So this has got to be progress, right? We're going from soft sciences to hard sciences, right? For people who believe in that nonsense. Okay, so here's the framework. But physics does have a lot of good paradigms for us to think about. Okay, so we start with a data structure D0. Okay, and now operation I transforms di minus 1 into di. So the ith operation you can view as a mapping. It takes the data structure and transforms it into a new data structure by whatever that particular operation does. And the cost of operation I is c sub I, just as before. Okay, the true cost. So what we do then is we define a potential function phi that maps the set of data structures into the real numbers such that the potential of the initial data structure is 0, okay, and the potential of any data structure is greater than or equal to 0. Okay, for all I. So if you think of the potential function as saying, what's my bank account? We're just saying your bank account starts off at 0, and it's always non-negative. You never had a negative balance. Okay? So we're sort of going, as I say, backwards from the from the accounting method, where there we assign a cost to each operation and then show that the bank account never goes negative. Here we start out with a potential function that has the property that it's never negative. And now we look at the amortized cost C sub I hat with respect to phi. So always when we talk about amortization, the way that we assign the amortized cost is our choice at some level, okay, subject to the constraints, okay? And same thing here. We take a potential function, but it's all with respect to that potential function, okay? So that's going to be C sub I hat, and that's going to be the true cost plus phi of di minus phi of di minus 1. Okay, so we add in the new potential, subtract off the old potential. Okay, and this is called the potential difference. And we'll use the notation that this is delta phi sub I, okay, for the potential difference. So let's take a look at what this formula means to understand it a little bit. Okay, what happens if delta phi I is greater than 0? What does that imply about the relationship between Ci and Ci hat? Yeah. Ci hat is greater than Ci. Okay, why is that? Well, if this is greater than 0, then Ci hat has got to be bigger than Ci. Okay? So what does this mean when I do operation I? What's happening? I'm saying that the amortized cost is bigger than the true cost. So what I'm doing then is charging more for the operation than it costs me to perform it. And hence, I'm going to have some of the fee that I've charged left over and dump that into the potential. Okay, so here, the operation I stores work into the data structure. For potential later use. Yeah? Well, in this case, if it's greater, if it's equal to, then it's not storing anything in. It stores 0 in. But if it's greater than, then it's. Now let's take a look if it's less than. And I'll let you figure out what happens if it's equal. Okay? So if it's less than, okay, then obviously Ci hat is less than Ci. Okay? And so what's happening here? How about somebody sleeping in the back? I think there's only one. There's 2 people sleeping in the back. No, 3. 1, 2, 3 people. Oh, no, 2 sleeping. Oh, 1. Oh, nobody's sleeping anymore. Yay. Okay. Yeah. You weren't sleeping. It doesn't count. No, that's okay. Go ahead. Answer. Go ahead. Yeah, what happens?
It's going to use the stored structure to pay for the cost?
Yes, it's going to use the stored potential now to pay for the cost of this operation. Okay, so the data structure delivers up stored work to help pay for operation I. Okay, so it delivers up the stored work. Okay, so now we get to do some math. Why is this a reasonable scheme? So the total cost of, total amortized cost of n operations is the summation I equals 1 to n of C sub I. And that's just the sum just by taking that formula and summing both sides. I equals 1 to n of Ci plus phi of di minus phi of di minus 1. Okay? And now we can do some math. Okay? So what am I going to be able to do here? What's the one word from mathematics that says how I go to the next step here? It's also a word from astronomy. Telescoping. Telescoping. Notice that each term here is added in once for I having one value and then subtracted out for I having the next, except the first and last terms. That's telescoping. Okay, remember this from calculus or wherever they teach that these days? Of Ci plus phi sub n is added in but never subtracted out. Whoops, phi of dn. Okay? And phi sub 0, phi of d0, is subtracted out but never added in as I go make the sun range through these values. Okay, so telescoping. So this is telescope. So even astronomy, we're doing physics. We're doing real physics here, hard science. Physics and astronomy and mathematics. All right. This is not a soft science. Okay. So what do I know about phi of dn? It's greater than or equal to 0. That's greater than or equal to 0. What about phi of d0? That's equal to 0. So what do I know here? Yeah, amortized cost is greater than or equal to the sum of the true costs. Hey, that's good. That means if I use the amortized costs, it gives me an upper bound on the true cost. That's what I want. Okay? So in the potential method, we assign potentials, and we derive the other one. So let's do that for table doubling. And this is where the potential method gets really hard, because and where you sort of have to really play in practice, in trying to apply this type of analysis when you sit down to do it. You have to really play with what the potential function might be. Okay? So for table doubling, dynamic tables, we're going to define phi of di to be 2I minus 2 the ceiling of log I. Now, that was intuitive, wasn't it? We'll see why that's the case, because basically what we're going to be doing is this is going to essentially stay constant at a certain level after we've doubled tables, and every time we increase I, we're adding 2. Okay? And then as soon as we hit the next power, boom, we subtract off. As soon as we hit, this becomes an exact power of 2, boom, we subtract it off, and we end up with dropping the value down to 0 as we're paying for stuff. Okay? So the first thing to note as we get there, okay, the other thing we're going to do for simplicity, for our boundary case, is we're going to assume that 2 to the ceiling of log 0 is 0, just as a technicality. And now let's note that what's phi of d0? 0. That's good. And what is phi of di? Is it greater than or equal to 0 for all I? Yeah, because this is 2 to the ceiling of log I. That's always less than 2 times I. Less than or equal to 2 times I. Okay, it's actually, yeah, less than or equal. Good. Okay, so let's take a look. Okay, and so in some sense what I've got here, let's just take a look at an example. Let's take the case where I had 8 things, and let's say I've got a table of size 8 and it's filled in 6 places. So I've done 6 inserts. So what is this value here? So it's 2 times 6. So in this case, phi is equal to 2 times 6 minus 2 to the, what's the ceiling of log I if I is 6? 3. What's that equal to? 4. Okay, and what is the situation in the accounting method? I basically have it being 0, 0, 0, 0, 2, 2 at this point, right? Okay, so it's 4, same thing. It's describing my bank balance. Okay. Very good. So now let's calculate what the amortized costs are. So in some sense, by the way, you should be really skeptical about all this stuff, because I'm taking something that was really simple to understand at the beginning of lecture and gradually making it more and more complicated until finally by the end of lecture nobody will know what's going on. Okay? We're just analyzing the same thing. But the fact is that when you master these things, then you have a wider range of things you can do. And I take the easy things not to make it more confusing for you, but rather so that you have some intuition out of which to understand this. Okay. So amortized cost of the ith insert. Okay. So CI is CI plus phi of DI minus phi of D sub I minus 1. And that's equal to, okay, the true costs. Well, the true cost, we know what that is because we had that formula. It's cost to I if I minus 1 is an exact power of 2, and it costs 1 otherwise. So this is going to be equal to, therefore, I plus the potential difference. That's 2I minus 2 to the ceiling log I minus, 2I minus 1 minus 2 ceiling of log of I minus 1. Okay, close. If I minus 1 is an exact power of 2. And it's 1 plus the potential difference, same potential difference. Okay, otherwise. Okay? You can see how much simpler this is than the aggregate method. Okay, so now let's calculate the amortized costs for the particular values. Let's evaluate this hairy thing. We'll do it as 2 cases, which makes sense because we have 2 cases. Case 1. I minus 1, don't need parentheses there. Case 1 is that I minus 1 is an exact power of 2. Okay, so C sub I is equal to, and let me just recopy here so we can see what the math is as we're going along. Okay, so that's what it is when I minus 1 is an exact power of 2. But if I know I minus 1 is an exact power of 2, now I'm in a position to evaluate some of these hairy formulas. Okay? So what is that equal to? I claim it's equal to I plus, now here I have 2I, and here I have minus 2I minus 1. So what's the difference there? 2. Right? This term and this term. Okay, it's 2. And then minus, okay, the difference there. 2 to the ceiling of log I minus 2 to the ceiling of log of I minus 1. Okay? So that's equal to, I claim, I plus 2 minus, well, what's this value equal to? Actually, this one's easier to go for first, right? This is just I minus 1. And what is this term equal to then? So I minus 1 is an exact power of 2. I? 2 times I minus 1. Because this is 1 bigger now than this. So this is twice that. Excuse me, this is 1 larger than that. So therefore, it's twice that. So what's that all come out to be equal to? So 2I minus 1 minus I minus 1 is what? I minus 1. I plus 1, excuse me, I plus 2 minus I minus 1, the whole thing comes out to 3. Hallelujah. Hallelujah. Okay, the other case. Okay, so case 2, I minus 1 is not an exact power of 2. So C sub I hat, once again, is equal to, just copying from the other board, okay, it's this mess. Okay, and so that's equal to 1 plus, well, we still have the same 2 here, minus 2 to the log I minus 2 to the ceiling of log of I minus 1. And what's that equal to now? So I minus 1 is no longer an exact power of 2. So how do these exponents compare? If I minus 1 is not an exact power of 2. They're equal. Well, if the exponents are equal, that means this whole thing is 0. So this is equal to 3. Okay. So therefore, if the amortized costs are order 1, that is 3 for each one, then n inserts cost theta n in the worst case. Now, there's a bug in this analysis, okay, which is I didn't actually properly handle the first insert. Okay, so that's a good exercise to go through and figure out where that bug is. Okay, let me just make a couple of quick conclusions. One is amortized costs provide a clean abstraction of data structure performance. That's the whole point. They give you a very simple, can give you a very simple, clean abstraction of performance rather than the complicated thing that might actually be going on inside a data structure. Okay, any of these methods can be applied typically in a situation, but some may be easier depending upon the situation, which means you have to learn them all, okay, if you want to make it easy. And different amortized schemes yield different bounds. One last thing is the recitation on Friday is extremely important. So I know most of the people here probably go because you're showing up to class, okay? So if you tell your friends, on Friday the material that's presented is not in the book, and it's crucial. And it's fun. It's amazing. Okay, it's one of the most amazing simple analyses there is. So please show up to recitation this week if you care about learning about algorithms. If you don't care about learning about algorithms, do whatever we want.